material is able to fully transfer, okay, penetrate. So through the thin film diode, okay, is a thin film diode, and then reflect. So you can see this is like a pyramid structure surface. So this is projection. So this kind of the surface you also can use in the simulation to create what kind of the surface morphology can be attract the optimal light absorption. Okay, light absorption. So this is some example that you can take some reference. So this is a surface texturing, just like for example here is a surface simulation data that we can do. Is a simulation. So this is a flux. Okay, it's a flux. Okay, flux that means attract light on the surface. So for example, you have a structure like a raw-like structure, okay, on this surface. So you can see on the tetra surface of this raw-like structure, there is more flux, which means higher potential. Okay, higher potential. So this higher potential demonstration that there's more light being attracted, okay, being trapped, okay, on the surface, So here it's just a normal surface that you can use in just what I explained on last class. Is you can drop the silicon to something like HF solution. So you can create like this is a tetra structure, a pyramid. Okay, this is a pyramid. So this pyramid that enable to travel more the light, okay, more the light through the solar cell. Okay, so on the backside surface we also can create a tetra backside. Okay, similar situation. Okay, similar situation. So this is another case. Okay, another simulation that this paper. Okay, this paper. If you are interested, you can search this paper. So this is coating with the just also similar to the tetra structure, a raw-like structure right here. And this is the surface. Okay, this is the surface. So this is the energy density. Tell you that with the carbon coating, on this surface. Okay, this is the carbon enlarged images right here. So you can see they deposit a carbon on the tetra surface, and then you can see here is the energy density. Okay, energy density. So if you think about the carbon coating, the energy density is reduced. Okay, it's reduced. So that means that light reflect is getting low. Okay, light reflect is getting low. So this is another case that tells us that after deposit this kind of anti-reflection or something like a tetra surface, what we can see that we can increase the light absorbed on the surface. Okay, light absorbed on the surface. Okay, so this is a reflectance ratio. Okay, reflectance ratio that, for example, we have the case 1, case 2, 3, and case 4. Okay, case 4. With the mirror surface of the silicon. Okay, that means without any coating, without tetra surface, so you can see there is a reflectance is right here. Okay, but the second case, okay, if we deposit anti-reflecting layer on the surface of the silicon, okay, for example at the 500 nanometer, so you will get the 500 nanometer, you get the lower reflectance. Okay, and case 3. Without anti-reflection coating, you have the tetra surface of the silicon. You can see they still can reduce the reflectance on the anti-spectrum. Okay, on the anti-spectrum for the case 3. This is without anti-reflection coating, but with the tetra silicon. So you have this spectrum. But when we deposit the anti-reflection layer with the tetra surface, you have the completely quite low. This can spectrum can reduce. So this is what we have to apply. So according to this kind of the design, actually we can optimize or increase the conversion efficiency of the solar cell. Okay. So this is the solar cell that we already showed you in some previous slide. Okay. So from the income to the module. Okay. From the income to module, for example, polycrystal, you can cut into the income. Okay. Just brick. Okay. And then you can cut into the wafer, slide to slide. Okay. One slide, two slide. And then diffusion. Okay. Diffusion. And then screen printing to make a wiring metal contact, okay, current collector. And then you encapsulate by regions, okay. So because we have to protect the solar cell surface, so we have to using the protective same thing and the glass, okay, and the glass on the top surface. But you may curiously ask me, Professor, so if we encapsulate the glass on the solar cell surface, will the surface reflection, that I would say the reflectance will be increased? Yes, of course, because this layer, okay, this is we have to do. Without this layer, without this protection glass, solar cell is very weak. It's easy to damage. Okay, so you have no choice. Of course, you have to do, because the solar cell you have to put for a long time, about 20 years, 25 years. So there's no way you have to do. Okay, so usually this protection surface glass will reduce 1 to 2% of efficiency will reduce. Okay, maybe more. After that, we making an array. Okay, making an array. Okay, this is a strength. Okay, glass. Okay, so this is slide is show you about some of different coating. For example, we can coating layer 2 or 3 preservation layer, and also silicon nitride anti-reflection layer. Preservation layer, later on I will show you why we need the preservation layer. Okay, and this is another preservation layer. Okay, we deposit on this side to increase the solar cell conversion efficiency. So for here is a slide show you that for the polycrystalline, actually we have to there's some lost silicon. For example, you have the 242 kilo. Okay, this is the crucible. Okay, this is the crucible, and then surrounding the area of the crucible, actually the solidification rate is different, right? Solidification rate is different. Solidification rate, once we have, because you have to melting, you have to through the pathology of the silicon to the crucible and then increase the temperature, right? So on the surface of the crucible area, there's a lot of I would say the defect because solidification rate is different. So therefore, we have to cut surrounding area. We have to cut on the 6th plane on the top side, surrounding on this circle, and also bottom side. So the materials will be lost. The materials will be lost. Okay. So based on this loss, okay, based on this loss, you can see this is the casting process. You can see, for example, this is the pull to this crucible. We heating the silicon in the molten state and pull out to this crucible, and then current like to crystallize the silicon. Okay, so this is for small volume of the crystal, but you still need to lose the 6 area, right? You have to lose this end, this plane, this plane, this plane, and top plane. Totally 6 plane, right? 6 plane. So in order to reduce the loss of the silicon, so what you can do? For example, you want to do the casting, right? You have to do the casting, and you have a molten state, okay, molten state of the silicon, and then pour to this crucible, right? This crucible. But surrounding on the crucible area, there's a huge number of defects. Later on I will show you, there's a huge amount of defects. So we have to cut out of the crucible area, right? So how to increase the throughput? You know the throughput. 如何增加产率? How to increase the throughput? That means how to increase maximum the production, the product. Very easy. You just increase the size, right? Increase the size. Because the same area, you have to cut. For example, the same area you have to cut, right? You just increase the size. For example, you increase the size. Here, this is the bridgement. Let's just show you the video, right? The bridgement process, solidification, heating, exchange method. Here, you can see this is the crucible, right? This is the crucible. This crucible move. Here is the inductor, right? Inductor. So once the crucible drop, move to this way, and then because left away from the heater, so therefore here become from the liquid to the solid. Here is the interface, right? And then if we increase the size more, right? So you can fix this brick, okay? Crystallized silicon is right here, and then we move the coil, right? You move the coil, right? So you have the bigger size. So you can look like that. For example, you have 270 kilo, right? And then to 300, right? So you cut here, you can cut, right? So that means if I increase the size, which means I can increase the throughput. Understand? I can increase the throughput. So this is the situation that increase the high yield. If you look at about the defect versus the conversion efficiency at the concession, okay, let's look at about it. Okay, this is a crucible area that you can see. There's based on the simulation, you can see there's a lot of the defect. Okay, a lot of the defect surrounding on this area. So this is electron lifetime. Okay, electron lifetime. Based on this here, the center area has a higher electron lifetime, but this area has a shorter lifetime, which means that once the electrons separate, or the carrier charge separation, and then it will be trapped and in this area, because this area has a lot of defect. Okay, if you look about the cross section, okay, this is the cross section height of the brick. This is a cross section. Here is the efficiency. You can see the efficiency surrounding near the surface of the crucible. You have the very low efficiency, right? And then if we look about the central area of the brick of the silicon, you can see the efficiency is much higher, right? It's much higher. So on this area, the efficiency is low. So therefore, we have to cut it. Okay. So this is the saturation that the silicon, polycrystalline silicon, could lose. Okay, could lose the some of the parts. Okay, need to cut it. Okay. So one of of the situation that we can do is some of the critical parameter of polycrystal silicon. Okay, because to grow a silicon, single crystal silicon, it takes Tchaikovsky, for example. We need to take 48 hours, right? 48 hours, and in 48 hours you get the single crystal chunk, single crystal silicon. We still have to cut bottom, top and bottom side, because the top and bottom side has also highest impurity, and also there's a higher, I would say, dislocation, okay, defect. Okay, and then we have to polish the surface of the silicon. So this kind of the single crystal, takes time and they're more expensive. So people, scientists, they will think about that if I can do is to purify the polycrystal silicon. Do you understand? Polycrystal is polycrystal, it's okay. But I just purify the impurity, just to get ultra high polycrystal silicon, ultra high purity of polycrystal silicon. Do you understand? Such we can do. Okay, so you can minimize, okay, the impurity, minimize the defect. Okay, although they still have polycrystal grain boundary, right? This is polycrystal grain boundary, but still I can obtain maybe this is 6N, about 6N, even 9N, right? Even 9N. So I can maintain the high purity of the silicon in this area, right? And even in the grain boundary, we can minimize the impurity, okay? We can minimize the impurity. Still, we can reach the high conversion efficiency, okay? And this case is passed to the, for example, you can do is the raw refining process. You can purify the polycrystal. You can purify the polycrystal. So this is a crystal defect in the ingot manufacturing to get more high efficiency solar cells. So that's why if currently single crystal and polycrystal silicon, the conversion efficiency is just approximate maybe 3 to 5% difference. Okay, 3 to 5% difference. The higher maybe up to 5% difference. But if we can minimize the impurity of the polycrystal, maybe we can reduce the distance of the conversion efficiency with the single crystal, maybe reaching maybe just only 2% less. Okay, understand what I mean? Okay, so this is what we can reduce the cost. Okay, reduce the cost. Okay, preservation. Okay, preservation. Preservation is also very important process that you have to do. Is for example, because we in previously we have talked about there's a fear factor, right? There's a fear factor. So surrounding this area, okay, you have the fear factor. For example, you have fear factor 1, right? And this area, fear factor 2. Of course, this area is bigger, right? So fear factor is high, right? So fear factor has involved a lot of issues, okay, a lot of issues, including the defect, okay, including some of the defect. If you have a large number of the defect, you have lower fear factor because of recombination rate increase. Okay, recombination rate increase. For example, like there's a defect. Like there's a defect. This is a moment. is moved to here. Because is suitable for me. Okay, for example, let's say we wanted to thinner the silicon, right? Thinner the silicon, and then usually on the bottom side we deposit aluminum electrode, right? Aluminum electrode. On the top side, you may have a case silver electrode, right? Silver, for example, this case. And then here you have the defect segregation, right? You have defect segregation, right? So it becomes sharp, right? It becomes sharp. That means the electron hole pair, that the top side electron, bottom side electron will contact, right? Based on this channel, So we call this might be, even we don't shine the light radiation, you still have the current being generated, right? So this looks like a dark curve, right? This is the major issue that causes the fear factor is low, right? Low fear factor. Okay, so there's many cases. Okay, this is one of the cases that if there's a defect segregate, okay, just penetrates through the anti-film, okay, or the anti-substrate, okay, you could get such a case. Okay, you could get such a case. So the defect, minimum defect is quite important. That you can see, we call this point. Okay, this point is the leakage current at the grain boundary in polycrystalline. This is a thin film, okay, HF, polycrystalline HFO oxide. Okay, just take one example to show you. So a lot of the grain boundary that we have to investigate, okay, because for example, if we look at about the characteristic IV curve, it looks like the fear factor is quite low, and then we have to further to investigate about the surface structure, and also maybe to investigate about the IV curve, okay, and maybe we have to cut a cross-section to investigate about the TM, okay, to see the TM about the sinking structure's duration, see what is the main cause, okay, what is the main cause. So another way to optimize the IV curve, okay, the IV curve. This is an example to show. Usually, for the solar cell, we have the 10 centimeter square multi-crystalline weight. Okay, so here I especially emphasize that if we want to increase the conversion efficiency, one of the ways is increase the grain size, right? Because the large grain size, the less volume of the grain boundary, right? The less volume of the grain boundary. So the less volume of the grain boundary, the highest conversion efficiency, right? So what we can do is because maybe some of the recycled single crystal silicon we can crush, recycle. I mean the recycled single crystal, maybe crush from the semiconductor somewhere else, and then we can prepare. Okay, we can prepare such situation, or you can base on certification process, because the certification rate is different, right? When you increase the temperature to about 1,400, right? That is the molten state, right? It's the molten state. So to cooling to the solid state of the silicon, the cooling rate is quite important, right? You can reduce the cooling rate in order to get the higher grain size, right? So the cooling rate you can control to get the high crystalline, to have the more time, okay, to get more time to grow, okay, because this is based on certification, right? You can control the certification time. Right. For example, at the T1, you have the T1, you have the nucleation, right? And then after T2, you get the nucleation increase, right? Nucleation growth is increased. So you can have the difference growth rate, right? You have the different growth rate, you could have the different grain size, right? You have the different grain size. So this grain size, this is also allow a single grain, okay, to extend, okay, from the front side to the back side, okay. So provide less resistance, okay, less resistance, in order to carry flow and decrease the length of grain boundary. Anyway, just reduce the grain boundary area, okay, reduce the grain boundary area. And then there is a very important so-called dangling bond, okay, dangling bond. Here is the silicon. So every single silicon share 4 electrons, okay, share 4 electrons. So there's a covalent bond, right, tightly covalent bond. But during certification process, they might have some of the area or the surface without silicon. So-called here is the dangling bond. So any defect or impurity, okay, at the surface or the grain boundary as well, this promote recombination, okay. So this dangling bond not only on the surface but also on the grain boundary area. You can also observe on the grain boundary area for example, this bond, unbound. Dangling bond. This is unbound. Okay? And then this is on the surface. Okay? So this particularly at a recombination center. Okay, recombination center. So preservation, how to do is we can deposit, for example, a thin layer, okay, a thin layer like a silicon dioxide, okay, deposit a silicon dioxide. This silicon dioxide not only add a preservation layer, but also you can add as an anti-reflection coating. Understand? There's a bifunctionality, which means that you can cover the dangling bond, right, on the surface, and also you can use this layer as an anti-reflection layer, okay, anti-reflection layer. So that's why here, okay, here we have Al2O3, okay, aluminum dioxide is an anti-reflection layer coating. Okay, preservation layer coating, And then this is a double. They not only Al2O3, Al2O3, they deposit another layer anti-reflection, so-called double layer. But Al2O3, if you didn't deposit silicon nitride, Al2O3 layer not only will act as a preservation, but also it can act as an anti-reflection coating as well. So this is the process, okay? So you can have having this randomly equivalent, okay, tetra structure, and then preservation, okay? For example, this is a preservation layer deposit, and then there's another layer, okay? Molybdenum, molybdenum oxide, okay? Molybdenum oxide. This molybdenum oxide is another preservation layer, okay? And then on the front side, we deposit AR coating, okay? AR coating. So you have a preservation layer to reduce the dangling bond, okay? To reduce the dangling bond. So there's a more popular process that we can do, okay? Surface preservation is to reduce the dangling bond. For example, here, there's a trapping site. Here is a trapping site, okay? The silicon surface, okay? The silicon surface, silicon atom are missing. There's a missing silicon atom. So, and then unpaired valence electron existing in here, okay? But after oxidation, okay, for example, you could do the oxidation. So you can have it, some of the oxygen in tight bond or tight on this surface, but still have the trapping site. Okay, you have the trapping site, and then you can coating, not a coating. You can pass this substrate or the same thing to the annealing process under hydrogen gas. Okay, under the hydrogen gas. So hydrogen could bond on this surface. Okay, bond on this surface. So therefore, some of the area that you can tight, okay, by oxygen and also by hydrogen. Okay. By oxygen, you will increase the resistance. Okay. By hydrogen, will be more better. Okay, will be more better because it won't be increase the resistance. But the bonding energy, silicon and oxide is more high bonding energy, right? Because silicon oxide, right? There is a strongly bonding energy. Okay. But silicon and silicon hydrogen has a weaker bonding energy. Okay. The weaker bonding energy, there is a weakness, so-called once this shining by light radiation, like a UV light, for example, and then the UV could cut the bonding between silicon and hydrogen. So therefore, the hydrogen will disappear again. So therefore, form the dangling bond again. Right? Do you understand? So some of the amorphous silicon, okay? You know the amorphous silicon. I will say here there's some example. Okay, here. This is the amorphous silicon. Okay? It is easy to observe dangling bond in amorphous silicon. Okay, in amorphous silicon. And usually we use in hydrogen to preservate the dangling bond. So you could see here hydrogen, right? But this hydrogen, the binding energy is quite weak. So therefore, this amorphous silicon shining the light radiation, for example, in the outdoor, all right? So there's a UV light, okay, UV light. UV light radiation is a very strong power. So it will cut the hydrogen atoms. So the hydrogen atom will mix, right? So and then form a dangling bond again. So that's why usually amorphous silicon has a maybe the conversion efficiency is 1/2 of silicon, just 10%, for example, or not 10%. But it is the lifetime is only maybe less than 10 years. Okay, and then even 5 years or maybe 1 year, you will dangling bond will easy to create. So therefore, the efficiency dropped a lot Okay, efficiency drop a lot. So this is hard to maintain. Okay, hard to maintain. So anyway, to do the preservation of the silicon, the hydrogen is the good way. But if you use in the oxygen, you will increase the resistance. You understand? Increase the resistance. Okay? So you can use in the, for example, this A silicon. This is amorphous silicon, and then hydrogen preservation. Okay, amorphous silicon using the hydrogen preservation. Okay, so you can mix by NH3 ammonia gas, right? Ammonia gas is easy to dissociate, right, to the hydrogen, right, to the hydrogen, and by CVD process, in very short time, okay, very short time. So you can increase the lifetime, okay, lifetime. Or this is a compare, or increase in the lifetime of the CSI is crystal. Crystal and silicon. Okay. An increase in the lifetime of the crystal and silicon wafer of at least 3-4 something, okay, or about 20 microsecond compared to a lifetime of 6 microsecond for a comparable crystalline wafer prepared without this method. Okay, so that's very important, right? With this method, you can increase the lifetime a lot, right? A lot. Okay. We have 5 minutes. Okay, just we take a break. Okay, 10 minutes to 35 to 25, and then we continue. Okay. We have the chapter 6. Did you receive chapter 6?